The concept of nothing has intrigued philosophers for centuries. It's a notion that dances on the edge of our understanding, challenging the very fabric of our thoughts and beliefs. From ancient Greek philosophers to modern-day thinkers, the idea of nothingness has been a subject of endless debate and contemplation. It represents the absence of everything we perceive, no matter, no energy, no space, no time. Imagine a void so complete that it defies the very essence of existence. This is the paradox of nothingness. It is both a concept and an anti-concept, something that exists only in its non-existence, a state of pure non-existence. But can we as beings of existence truly comprehend such a state? Our minds are wired to perceive, to understand, to make sense of the world around us. The idea of absolute nothingness is alien to our very nature, but can true nothingness exist? Science suggests otherwise. In the realm of physics and cosmology, the concept of nothingness takes on a different meaning. Even in the vast emptiness of space, there are quantum fluctuations, particles popping in and out of existence, and the ever-present fabric of space-time. In the realm of science, defining nothing becomes even trickier. The more we delve into the quantum world, the more we realize that what we perceive as nothing is actually teeming with activity. Virtual particles, quantum fields, and the mysterious dark energy all suggest that the universe abhors true emptiness. We can observe and measure the absence of things, like a vacuum. A vacuum in scientific terms is a space devoid of matter. But even a perfect vacuum is not truly empty. It is filled with potential, with the possibility of particles and energy. But even a vacuum, as we understand it, is not true nothingness. It is a seething cauldron of quantum activity, a place where the laws of physics still hold sway. The very fabric of the universe is woven with the threads of existence, even in the most seemingly empty spaces. It still possesses fundamental properties and forces that defy the idea of absolute emptiness. Gravitational waves ripple through the cosmos, magnetic fields stretch across vast distances, and the cosmic microwave background radiation permeates all of space. The human mind struggles to grasp the concept of nothing. We are creatures of existence, our thoughts and perceptions shaped by the world around us. The idea of nothingness is a challenge to our very understanding of reality. We are beings of existence, hardwired to perceive and interact with the universe around us. Our senses, our thoughts, our very being are all attuned to the presence of something. The notion of absolute nothingness is a profound and perplexing paradox. But the more we delve into the fabric of reality, the more we realize that nothing might be an illusion. The universe, in all its vastness and complexity, may never truly allow for the existence of absolute nothingness. It is a concept that challenges our understanding, pushing the boundaries of our knowledge and imagination. Often we use the terms vacuum and nothingness interchangeably. This common misconception arises from our everyday experiences and the way we casually talk about empty spaces. When we think of a vacuum, we might imagine a completely empty room or the void of outer space, devoid of any objects or matter. However, in the scientific context, they hold distinct meanings. Scientists have precise definitions for these terms, and understanding the difference is crucial for grasping the complexities of the universe. A vacuum refers to a region of space devoid of matter, like the vast stretches between stars and galaxies. These areas might seem completely empty to the naked eye, but they are not truly void of all substance. While a vacuum might appear empty, it's far from being nothing. Even in the most desolate parts of space, there are still particles, radiation, and quantum fields that permeate the environment. Even the most perfect vacuum we can create in a laboratory still contains residual particles and fields. These remnants are a testament to the fact that achieving a state of absolute emptiness is practically impossible. This is because space itself is not empty. It is filled with fluctuating energy fields and virtual particles that pop in and out of existence, a phenomenon predicted by quantum mechanics. True nothingness, on the other hand, would imply the absence of not just matter but also space, time, and even the laws of physics themselves. This concept is almost impossible for us to fully comprehend, as it defies the very fabric of our understanding of reality. It's a concept that challenges our understanding of reality. The idea of absolute nothingness is more of a philosophical or theoretical construct rather than a physical state that we can observe or measure. So, while a vacuum represents a low-energy state, it's crucial to remember that it's not the same as absolute nothingness. A vacuum still has structure and properties that can be studied and understood. Whereas true nothingness remains an elusive and abstract idea, it's merely a stepping stone in our exploration of the universe's most fundamental mysteries. As we continue to study the cosmos, the distinction between vacuum and nothingness will help us unravel the deeper truths about the nature of existence and the origins of everything we see around us. Quantum physics, the study of the very small, throws a fascinating wrench into the idea of nothingness. It tells us that even seemingly empty space is a roiling sea of quantum fluctuations. These fluctuations are governed by the laws of probability and uncertainty. These fluctuations give rise to what we call virtual particles. They are pairs of particles and antiparticles that constantly pop in and out of existence, borrowing energy from the vacuum itself. They exist for fleeting moments, annihilating each other and returning the borrowed energy. This phenomenon might seem counterintuitive, but it has been experimentally verified. The existence of virtual particles demonstrates that even a vacuum is teeming with transient energy, making true nothingness an impossibility. Section 4: The Casimir Effect, Proof in the Pressure. One compelling piece of evidence for the existence of energy in a vacuum comes from the Casimir Effect. This fascinating phenomenon has intrigued scientists for decades, providing a window into the mysterious world of quantum mechanics. The Casimir effect is named after Dutch physicist Hendrik Casimir, who first proposed the idea in the mid-20th century. It has since become a cornerstone in the study of quantum field theory. This phenomenon, predicted in 1948 and later experimentally confirmed, demonstrates that even in a vacuum, there exists a pressure exerted by virtual particles. These virtual particles are transient fluctuations that pop in and out of existence, a concept that challenges our classical understanding of empty space. The Casimir effect is a tangible manifestation of these quantum fluctuations. Imagine two perfectly smooth plates placed very close together in a vacuum. These plates are often referred to as Casimir plates. The distance between them is so minuscule, often just a few nanometers, that it creates a unique environment for virtual particles. The space between the plates is restricted, allowing only certain wavelengths of virtual particles to exist. While one might expect no force between them, the Casimir effect shows that the virtual particles surrounding the plates create a net inward pressure. This pressure is a result of the imbalance in the number of virtual particles between the plates and those outside them. The particles outside the plates exert a greater force, pushing the plates together. This is because the plates limit the wavelengths of virtual particles that can exist between them, while particles on the outside exert pressure inward. The wavelengths that can fit between the plates are fewer and shorter, leading to a lower energy density between the plates compared to the outside. This difference in energy density results in the plates being pushed together. This pressure, though tiny, has been measured and confirms the presence of energy in seemingly empty space. The force is incredibly small, often measured in micronewtons, but it is a significant proof of concept. Advanced instruments and meticulous experiments have allowed scientists to measure this minute force with great precision, further validating the predictions of quantum field theory. The Casimir effect serves as a stark reminder that a vacuum is not nothingness, but a dynamic environment teeming with quantum activity. It challenges our perception of emptiness and opens up new avenues for research in quantum mechanics and cosmology. Understanding this effect not only deepens our knowledge of the quantum world but also has potential applications in nanotechnology and other advanced fields. Section 5. Energy's Dance, Never Created, Never Destroyed. The concept of energy conservation is a cornerstone of physics. It states that energy cannot be created or destroyed, only transformed from one form to another. This fundamental principle has profound implications for our understanding of nothingness. If energy cannot be created, then it must have always existed, even before the Big Bang. This challenges the notion of a true beginning where there was absolutely nothing. It suggests that the universe might have emerged from a pre-existing form of energy. Furthermore, if energy cannot be destroyed, then it implies that the universe cannot simply cease to exist, collapsing into nothingness. Even if all matter were to disappear, the energy it contained would persist, perhaps in a different form. Section 6. The Big Bang, From Singularity to Universe. The prevailing cosmological model suggests that the universe originated from an incredibly hot, dense state known as a singularity. This singularity, often described as a point of infinite density, is thought to have contained all the energy and space-time that make up our universe today. While the Big Bang Theory doesn't explain what caused the singularity or what existed before it, it does suggest that the universe arose from a state of extreme energy concentration, not from absolute nothingness. The Big Bang Theory, while the best model we have, raises more questions than it answers. It pushes the boundaries of our understanding of physics and forces us to confront the limits of our knowledge about the true nature of reality.